Today I will be observing falling motion using Newton's first law of motion, which is about uniform motion, and then an object will not stop its motion or will stay in rest unless acted upon by an outside force. But in this case of falling motion, gravity and drag force are two forces that act on the object, so it does not contain uniform motion. But Newton's second law states that force equals mass times acceleration, and this is seen here on the tracker. Here is the tracker file. If I play the clip, we can see the ball falling and the points plotted. Here's the graph shown, which shows a curved graph and then slowing down into somewhat uniform velocity. And this is plotted with the y direction. And here is my scale. It was held against the ball that I used. If we look at these values in here, the x component does not matter as we are looking at the y values of motion. In order to make a computer model of this, I set those values in VPython, and here are my initializations, the ball's mass, as well as the ball's position and velocity vectors. And the ball is starting at the origin, as can be seen right here. And the velocity, the initial velocity of the ball is 0 because it is starting off being held. And my delta t is a small time step in order to be as small as possible. Here's the gravitational force constant, weight force constant, and here's j hat vector to show the direction of the positive direction axis. And here my time step is 0.44 seconds because my total time as my video was 0.433 seconds. Here I've added the weight, which is mg, so the ball's mass times gravitational force constant. And here initially my computer model just uses net force of the weight, and we'll consider drag later. My initial model showed that as the object fell, it kind of matched up with the graph, but there's some discrepancies over here and over here, and where in order to fix this, we know that the model does not account for drag forces. So I tried to fix that by using a few different values for B, and I tried to get close to the end position, so it's kind of forcing it to match up. And my B value that I got was 0.00041. It's a very small force of drag, and I used turbulent force to calculate that. And turbulent velocity is calculated by negative b times the magnitude of the ball's velocity times the ball's velocity. And this is seen here in my code, and we add that to the weight to get the net force. Again, here is Newton's second law written into my code, as well as finding the next position. Now, if we run this code, as it loads, we can see that the graph shows the same thing we saw before in my other graphs. And here I've already set some aeroscale constants, which I'll show you in a second. But here's the force of gravity demonstrated here. And in comparison, we can see that the drag force arrow is very small. So in order to get these, I edited this bit here my arrow scale was 80, and I calculated this by using the fact that the weight of my ball, which again was 0.00521 kilograms, I used that against a arrow length of 4 meters, and I calculated a length of 4 meters over 0.05 newtons, calculated from the weight of the ball, and I got an arrow scale of 20 meters per newton. So when I add that into here, put that arrow scale in, here's arrow 1, here's arrow 2 for the weight and the drag force, and this is why it becomes such a small arrow compared to a gravity arrow. Here are all my tables with the model position data and the model position with drag, and the experimental position data is down here. And here's my graph, and we can see that the experimental position has some discrepancies here, and the model position with drag tried to help a little bit, but it still did not help the accuracy much. This may be due to some error factors in plotting my points on tracker, which might not be completely in line with the ball here, as well as some recording factors, as the ball may not have traveled completely straight. So from this graph, I can conclude that the model with gravity and drag force included helps predict the realistic experimental model a little bit better than the model position without drag force. And if I were to use a better model, such as dropping the ball from a higher distance, from a higher height, I would get a much better set of data. If I were to have a higher distance and I let the ball fall for a longer time, I would observe the concept of terminal velocity, where the force of gravity starts to equal the drag force, and where the velocity stops changing. I wasn't able to really get to that point in the graph here, but it would start looking like one straight line with a constant slope.